Pluto, the intriguing dwarf planet at the edge of our solar system, has stirred up excitement in the astronomy community. Recent reports hint at a possible close encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Prominent figures like Neil deGrasse Tyson and Michio Kaku have highlighted the potential consequences of this celestial event. But how did Pluto, once downgraded from full planet status, end up on a trajectory that brings it near Neptune? And what could this cosmic interplay mean for Earth? Let's dive into the details to understand why this event has scientists on alert. Pluto, initially classified as a planet, was later redefined as a dwarf planet due to its unique orbit. Despite this change, it remains a source of fascination in the astronomical community. Recently, scientists such as Neil deGrasse Tyson and Michio Kaku have raised alarms about Pluto's path potentially intersecting with Neptune's, sparking fears of an impending collision that could have significant effects on Earth. Pluto's orbit around the Sun is unique in many ways. Since its discovery in 1930, it has yet to complete a full revolution around the Sun due to its remarkably lengthy path, taking about 248 years for one complete orbit. Unlike the mostly circular orbits of major planets, Pluto's path is elongated and tilted at a 17 degrees angle to the ecliptic plane. This combination of its orbital tilt and eccentric shape means that, for around 20 years of each orbit, Pluto actually travels closer to the Sun than Neptune, a surprising occurrence given their positions in the solar system. One key aspect of Pluto's orbit is that it isn't a perfect circle but rather more of an elongated oval. This orbit results in Pluto experiencing wide fluctuations in its distance from the Sun. At its closest approach, Pluto is around 30 astronomical units (AU) from the Sun, whereas it reaches over $49 at its farthest, which is more than twice Neptune's distance from the Sun. Pluto's inclined orbit also influences its interactions with other celestial bodies, especially Neptune. When Pluto approaches Neptune's path, their gravitational forces influence each other, altering their respective trajectories over time. This gravitational interplay between Pluto and Neptune underscores the complex dynamics of our solar system. Although Pluto was once considered a solitary traveler in the outer reaches, its close encounters with Neptune reveal the interconnected nature of celestial bodies, each exerting gravitational influences that shape the paths of others. Advances in observational technology have allowed astronomers to track Pluto's movements with great accuracy, deepening our understanding of its orbit and its potential implications for the stability of the outer solar system. While the probability of a direct collision between Pluto and Neptune remains low, it cannot be entirely ruled out. Scientists have been closely monitoring Pluto's orbit to assess any possible disruptions. Despite its small size and distant location, Pluto continues to captivate both researchers and enthusiasts. One might wonder why there hasn't already been a collision between Pluto and Neptune. The answer lies in gravitational interactions with other planets. Pluto's orbit is not stable in the same way as the major planets due to its steep tilt and oval shape. Astronomers initially noticed Pluto's peculiar path because, unlike most planets that follow a similar plane, Pluto's tilted orbit stands out. Even though Pluto's path crosses Neptune's, these complexities don't lead to collisions because of certain gravitational relationships. Key terms like azimuthal libration and latitude libration describe how planets remain in stable orbits. Azimuthal libration, for instance, keeps planets like Pluto and Neptune safely separated by ensuring they are at least 90 degrees apart during their closest approach. Latitude libration, on the other hand, makes sure that when Pluto nears Neptune or other large planets, it remains well above or below their orbital paths, lowering the risk of a collision. The von Zeipel-Lidov-Kozai (VZK) oscillation, named after researchers who studied these effects, explains why Pluto's orbit, while unusual, remains predictable over time. Despite the seeming chaos in space, these gravitational mechanisms provide an orderly structure that keeps Pluto's orbit stable, preventing potential collisions with Neptune. Orbital chaos theory, which examines the sensitivity of a celestial body's path to its starting point, is vividly demonstrated with Pluto. Small changes in its position or speed could significantly alter its orbit over long periods. Through computer simulations, scientists can model how Pluto moves and interacts with other objects in space. By adjusting these simulations slightly, astronomers can see how small shifts in Pluto's initial conditions can lead to major changes in its path. In the 1980s, simulations revealed intriguing aspects of Pluto's orbit. Although it should be unstable due to various factors, the orbit remains eccentric and, in theory, stable. Yet even slight differences in Pluto's starting position or speed could yield substantial shifts in its orbit, underscoring the delicate balance that keeps Pluto and Neptune in a cosmic dance. That the academic community should continually monitor Pluto's orbit to prepare for unexpected changes as observational technologies advance. Although the likelihood of a collision is low, he supports ongoing research and vigilance, as even subtle shifts in planetary orbits can greatly impact our understanding of the universe. To fully appreciate the complexity of Pluto's orbit, it's essential to consider the different forces at play within the solar system. For example, the gravitational influence of large celestial bodies like Jupiter and Saturn also affects Pluto's path. These giants exert significant gravitational pulls, which can subtly alter the trajectories of smaller objects like Pluto. This interconnectedness of the solar system demonstrates how distant bodies can impact each other's orbits through gravitational interactions. Jupiter's immense gravity, in particular, can send ripples through the orbits of nearby objects, occasionally redirecting them in unexpected ways. Besides gravitational interactions, the presence of other trans-Neptunian objects, TNOs, and Kuiper belt objects, KBOs, adds further complexity. The Kuiper belt, located beyond Neptune, contains numerous icy bodies and dwarf planets, including Haumea and Makemake. The gravitational influence of these objects also contributes to disturbances in Pluto's orbit. Studying these interactions helps scientists understand not only the dynamics of Pluto's orbit, but also the broader structure of the outer solar system. One fascinating aspect of Pluto's orbit is its interaction with the solar wind, a stream of charged particles emitted by the Sun. Despite Pluto's distance from the Sun, the solar wind still affects its atmosphere. When Pluto's orbit brings it closer to the Sun, its atmosphere can expand due to the increased solar radiation, making it more dynamic. This interaction is a key reason why Pluto remains an intriguing object of study. Its atmosphere's response to solar changes offers insights into how distant celestial bodies interact with their surrounding space environment. NASA's New Horizons mission, which conducted a flyby of Pluto in 2015, provided a wealth of data that continues to shape our understanding of this distant world. New Horizons captured high-resolution images and gathered various measurements of Pluto's surface and atmosphere, revealing stunning details such as vast ice plains, towering mountains, and even potential signs of cryovolcanism. These discoveries have transformed our view of Pluto, showing it to be a geologically active world rather than a static, frozen relic. The complexities of Pluto's orbit and its interactions with other celestial bodies contribute to our understanding of celestial mechanics. Studying these dynamics enriches the field of dynamical astronomy, which explores how objects move under the influence of gravity. By analyzing the intricate dance between Pluto, Neptune, and other solar system bodies, scientists gain insights into the principles governing orbital mechanics and stability. This knowledge is essential for predicting the future movements of celestial objects and understanding the long-term evolution of planetary systems. In terms of planetary protection, studying objects like Pluto is also relevant. While Pluto itself poses no threat to Earth, understanding the behavior of smaller bodies in the solar system helps scientists develop strategies for monitoring and mitigating potential hazards from other objects. Lessons learned from studying Pluto's orbit can be applied to tracking near-Earth objects, NEOs, and forecasting their future paths, which is part of a broader effort to protect Earth from potential impacts by asteroids and comets. The academic community remains vigilant in observing Pluto and other distant objects. Future missions and telescopic observations will continue to refine our understanding of Pluto's orbit and its interactions with the solar system. Potential missions to other Kuiper belt objects could further illuminate the early solar system's formation and the development of planetary systems. Beyond its scientific significance, Pluto's story highlights the role of public engagement in space science. The reclassification of Pluto as a dwarf planet sparked widespread interest and debate, illustrating how scientific discoveries can captivate the public's imagination. Educational programs and outreach activities centered on Pluto and similar celestial objects help foster greater appreciation for the wonders of the universe, inspiring the next generation of scientists and explorers. Overall, studying Pluto's orbit and its potential interactions with Neptune offers valuable insights into the dynamic nature of our solar system. By continuing to explore and monitor these distant worlds, scientists deepen our understanding of celestial mechanics, planetary formation, and the broader cosmic environment. The ongoing research into Pluto and its relationships with other planets underscores the complexity and interconnectedness of the solar system, revealing a universe that is both fascinating and constantly evolving. Over countless years, despite occasional disruptions, Pluto's orbit remained stable for an incredibly long time, billions of years. This suggests that while Pluto's path might seem chaotic, its journey around the Sun follows a certain order. Predicting the future movements of objects like Pluto, which have irregular orbits, is challenging because these systems are so unpredictable that it's hard to forecast long-term outcomes. Simulations help us understand what might happen, but they also reveal that we can't predict everything perfectly. These models rely on precise starting conditions and complex dynamics, so even a small error can lead to vastly different results, making accurate predictions difficult. Understanding Pluto's orbit is essential, especially as we consider whether it might collide with Neptune in the future. This information helps us grasp the mechanics of our solar system. Pluto's orbit shows us that paths that seem erratic can actually be balanced by gravity, demonstrating how celestial objects move in space. Continued observation and study are crucial for understanding our place in the universe. When we explore space, we see how unpredictable things can be, and Pluto's orbit is a prime example of this unpredictability. Pluto's orbit differs from that of other planets. It's more oval-shaped, not a perfect circle. Times, Pluto even gets closer to the Sun than Neptune. This proximity could be risky because Neptune is also moving along its path nearby. There's a slight chance Pluto and Neptune could eventually collide, but for the most part, Pluto manages to keep a safe distance from Neptune due to gravitational forces. Gravity acts like an invisible pull between objects, so even if Pluto and Neptune appear to be on a collision course, their orbits are carefully guided by gravity's pull. Pluto's orbit teaches us that space is full of surprises. What appears chaotic may be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the complex mechanics of our solar system, and ongoing observation and analysis are vital for expanding our knowledge of the universe and our place within it. If Pluto and Neptune were to collide, it would be an unprecedented cosmic event, reshaping our understanding of the solar system. Despite advances in space knowledge, situations like this remind us how much we still have to learn. Studying how large planets influence Pluto's path gives us valuable clues about the functioning of our entire solar system. It shows us that each planet's position and movement can alter the paths of other objects in space. Although space is complex, some leading scientists worry about the small possibility of a Pluto-Neptune collision. Neil deGrasse Tyson, a prominent astrophysicist, has intriguing ideas about Pluto. He sees the reclassification of Pluto as a dwarf planet, rather than a major planet like Earth, as progress. Tyson believes we are constantly discovering new things about celestial movement. He views Pluto's unusual orbit as evidence that there's still a lot we don't know, which to him makes the mysteries of space all the more exciting to study. He also recognizes that major events like Pluto's reclassification spark public interest in astronomy. Tyson aims to help people understand the fascinating and sometimes strange mechanics of space, believing it's essential to discuss how these dynamics can surprise us. Working with other scientists, he highlights the potential risks of Pluto's unusual orbit, concerned that a future collision with Neptune could lead to significant issues for our solar system. An impact between Pluto and Neptune would be both extraordinary and intense, releasing massive energy and potentially breaking Pluto into fragments. Debris from the collision could scatter through space, possibly hitting other planets and moons, and Neptune's own orbit could be altered. Renowned theoretical physicist Michio Kaku considers a potential Pluto-Neptune collision as a rare yet monumental cosmic event. Kaku sees this scenario as a valuable opportunity for scientists to study solar system dynamics in detail. He suggests that while the chances of such a collision are low, the insights gained from examining such a rare event would be invaluable. Kaku emphasizes that understanding such events would not only deepen our grasp of planetary orbits, but also provide insight into the formation and evolution of our solar system.